In this video, I'll be covering the topic of Lagrange interpolation, which is another form of polynomial interpolation. So this is an alternative method to find interpolating polynomials. And here, instead of the general expression from the introduction of polynomials, or instead of Newton polynomials, we will use another format, namely Lagrange polynomials. So if we again have n plus 1 data points given by x0, y0, x1, y1, and so forth up until xn and yn, we can fit a polynomial of degree n through those data points. And the Lagrange polynomial is then given by this expression. Fn of x is going to be the sum of the terms Li times Yi for I ranging from 0 to n. As you can see, it is given also in the sigma notation. And this is the general expression for the Lagrange polynomials. And the functions L of x are given by this expression. And they are given by the product of x minus xj over xi minus xj for j ranging from 0 to the degree of the polynomial n. And j cannot be equal to I, because then the denominator would be equal to 0. So these are, again, the general expressions, and we can just plug in values and see what the first and second order Lagrange polynomials will look like. So the first order, n is 1, we will have an expression of a straight line. And it's going to be this. F1 of x is going to be L0 y0 plus L1 times y1. And then you can calculate the L functions like this. I think there's a y0 missing, but you have to multiply the first L term with y0 still. So the second order, n is 2, will be given by this expression. Now you have 3 terms that you will sum, and if you plug in the values, you obtain these L functions here and this general expression. So the main idea between Lagrange polynomials are basically that each L function is equal to 1 at x is xi, while it is equal to 0 at all the other data points. So you can see that this is depicted in this figure as well. This means that each product, Li times Yi, takes on this value of Yi at this data point xi. And here in this figure, the again second order Lagrange polynomial is depicted, going through 3 data points. And it is, recall, the sum of these 3 terms. And you'll see in this figure the 3 terms are plotted separately as well. So the first term goes through the first data point, while it is equal to 0 at the other 2. And similarly, you can see the second and third term are plotted as well. And if you sum them, you will have a nice polynomial going through the 3 data points. So it may seem a little abstract still, so we will discuss an example. So we want to find the Lagrange polynomial going through these 3 data points. Yes. So we have n is 3, and therefore our Lagrange polynomial is going to be of the order 2. So we have f2 of x is going to be equal to L0 times y0 plus L1 times y1 plus L2 times Y2. So this is just the general expression of the Lagrange polynomial. And recall that the expression to calculate these L terms is this. So it's the product of j ranging from 0 to n, so in our case 2, of x minus xj over xi minus xj. So now we can use this expression to calculate the L functions. So L naught of x is going to be, so we start, so I is 0, so j cannot be 0, so we'll start off with j is 1. So we'll have x minus x1 over x naught minus x1. And then we multiply this product with the product where j is equal to 2. So then we get x minus x2 over x naught minus x2. So this is just the general expression of the 0 function, and now we can plug in the values for x0, x1, and x2. So, because these are the x values of the data points. So, let me see. Let me write the data points up here as well. So we have these 3 data points, 4 and 1, and 5 and 6. So then the x1 is going to be 4, x2 is going to be 5, and x0 is going to be 1. So this is L naught. Then this is equal to minus 3. This is equal to minus 4. So this in total is going to be 1 over 12. Let's see if I have this. Yeah. So the final expression for the first L function is this. And then we can plug this in for this term. So let me just write down f2 of x is going to be L naught y naught plus. I will only do the example for this first term because the other 2 terms are similarly calculated. We have y naught is going to be 2, so we'll just have this function L naught times 2, so it's going to be 1 over 6 x minus 4 x minus 5 plus these 2 other terms that I will not be going over. But if you do that, you obtain this Lagrange polynomial. So indeed you can see this first term L naught times y naught is given here as well, and you can obtain in similar fashion the second and the third term. Usually you often you don't do this by hand, so here it is presented in MATLAB as well. 3 data points and the Lagrange polynomial going through the 3 points. So now let us discuss another example, namely the example from the last video on Newton interpolation, because we can use Lagrange interpolation to solve this question as well. So recall that we were given the thermal conductivity for the element mercury at 4 different points of temperature, and the question was to estimate the thermal conductivity at 600 Kelvin. So at a point in between, somewhere in the interval. So these were our results from Newton interpolation, the plot with the polynomial going through the 4 data points, and our estimated value for the thermal conductivity at 600 Kelvin. Now we can also calculate the polynomial with Lagrange interpolation. Just like we did it in the last example by hand, you can write a program that does it for you. And here, such a program is given with already the data points in it as well. And you basically have two for loops, namely the summation part, where you sum the terms to get the final polynomial. And the inner loop is for the product to calculate the L functions. So using that, we obtain this plot for the Lagrange polynomial going through the 4 data points. And as you can see, it looks really similar to Newton interpolation. And using this, we obtained this solution for the thermal conductivity at 600 Kelvin. So this is also very, very similar to Newton interpolation. So, to recap and to compare, Newton and we have discussed two methods of polynomial interpolation, namely Newton and Lagrange interpolation. Newton uses the finite divided differences, which you do not use for Lagrange. But this recursive nature of the finite divided differences makes it very useful to develop higher order versions with Newton interpolation. Because if you add a data point to your data set with Lagrange interpolation, you will have to calculate all these functions Li of x again. Whereas with Newton interpolation, you only have, you still have these finite divided differences, but you only add one. So overall, when you already know the order of the polynomial that you are going to fit through the data, both methods require similar computational effort, and Lagrange interpolation might be a little bit easier to understand the program, and you do not need to store the finite divided differences. However, when you do not know the order of the polynomial, Newton interpolation is generally a lot faster and more useful there.